This is the problem you have for number 1 on the Unit 6 review. It's just the basics, the very bare minimum that we want you to know about radicals. And so in this particular expression, I want you to recognize that this really only belongs to the x. A lot of times students think it also belongs to the 64. If it was going to belong to the 64, we'd have parentheses around these two terms with the 5/2 as the outside in the exponent position. So what do I do here? So if I'm going to rewrite this, I'm going to make my radical symbol. Remember, the bottom number always goes out front. And I have two choices that are correct.
Good afternoon, Bruins. Please pardon this interruption. All AP seminar students, please report to the community room at this time for your AP seminar exam. As a reminder for students at second lunch, the admin lobby will be closed during second lunch this afternoon. Thank you and have a great day.
This 5 will go inside or on the outside. So you have two choices. It can be correct to put it here on the inside, or you have the choice to put it on the outside. The 64, it's not directly impacting. The 64 would remain here. Okay, let's look at another problem like this. Okay, let's go with 16x to the 3/4. Again, because it's not in parentheses, this only impacts the x. 16 stands alone. I'm going to make my radical the bottom number, not the larger, not the smaller. The bottom number goes out here as this nth term. And I have the choice for the 3 to go inside, or I could put parentheses and put it on the outside like you see here. That is number 1. Now, number 2, we're going to reverse it. So number 2 gives us an expression that looks like this, and we want to put it into this form. So to do that, again, the confusion often is what goes on top, larger number, smaller number. That's not it. The nth number outside always goes on the bottom, and then this number, whether it is outside or inside, always goes on top. So to look at one more, if I gave you this, and I asked you to rewrite it in rational exponent form, we would have x raised to the nth term goes on the bottom, 13 goes on top. Okay, let's take a look at number 3. Let's take a look at number 3 next. So number 3 wants us to rewrite, and as we simplify, we're going to choose all the options below that are equivalent to this. So first, if I look at my options, now I'm going to start writing this in rational exponent form. That means we have an exponent that has a fraction. So the nth term always goes on the bottom. This outside term comes on top. So these two are equivalent expressions. Now this could also be reduced, both even, so this could be a 4/3. And then if I put it back into radical form, remember the bottom number goes here, and I have the option for the 4 to go in this place or parentheses and put the 4 outside. Let's do another one like this. Okay, so this is the expression. I'm first going to rewrite it in rational exponent form. 15 on top and 10 on the bottom. The nth root always goes on the bottom. I can reduce that, and I could use a calculator to reduce it. It reduces to 3/2. And now if I put it back into rational form, it looks like this. We have x, the nth term goes on the outside, and this 3 I have an option to put it inside, or I could put parentheses and put it on the outside. Those are my two options. This is going to be a mirror image of number 4 from the review. And remember, when you have the exact same base, which happens to be x, and you're multiplying, you're going to add the exponent. So what number is hiding outside? It is a 2. And what number is inside? It is a 1. So this is 1/2 plus, okay, what goes on the bottom? It's the nth term plus 2/7 plus 3/4. All over. Again, what number is here? It's a 1. So the nth root is on the bottom. Okay, so what do? I grab that calculator. Please mimic this if you're here in class or at home watching. And I'm going to put parentheses. I have 1/2 plus 2/7 plus 3/4. I'm going to turn it back into a fraction. So the numerator is equal to x raised to 43 over 28. So when you're multiplying, you add the exponents. When you're dividing, you subtract them. So I'm going to take that 43 over 28, and I'm going to subtract it from 1/5. Putting it back into a fraction, and I have 187 over 140. This is equivalent. It's the simplified answer to this original expression. I want to solve for the variable x. This mimics number 5 from the review, number 5. So not the same problem, but the same concept. So what unique value of x, if one exists, can I substitute it in on the left-hand side, and I evaluate the left, and it will equal -7? Is that a possibility? That's what we're doing right now. Okay, excuse me. All right, so I'm going to start by subtracting 5 to the other side. And now this is like a -1 out front, so I'm going to divide by the -1. I have a positive 12. And then I'm going to ask myself, okay, how do I get rid of a square root? How do I know it's a square root? If you don't see a number, it's a little hidden too. Well, I'm going to square both sides. So x plus 1 equals 144. I subtract 1 to the opposite side to get 143. Now, how do I know this is the correct answer? I can take 143 and come back up here. 143 plus 1 is 144. The square root of 144 is 12, and 5 subtract 12 is, in fact, -. This is like number 6. There's a couple different ways you can look at this. Some people feel most comfortable rewriting this right away. So remember, the nth root here is 3, so 1 over 3. Now we want to isolate for x to see, is there a number I can substitute on the left, and the left side will equal positive 4. So to do that, we need to do the same thing to both the left and the right. I'm going to multiply by the reciprocal, so 3 over 1, which is the same as 3. They don't just cancel out, they simplify to 1, and I have 16x equals, okay, what is 4 to the third? You can look at that sheet. Some of you already know your numbers. It is 64. And now I'm going to take 64 and divide it by 16 to get 4. So if I substitute this in and I take 16 times 4 to get 64, I know that the cube root of 64 is 4. That is a... This question mimics number 7. This question mimics number 7. So I want to solve for x such that the left side equals the right side. So remember, I'm going to come back to this problem. I just want to make sure that it is untouched. So what is this number? It is a 2. So the square root, to get rid of that square root, I'm going to square both sides. So I have x squared equals 1x plus 12. My suggestion is always to move things to the same side as the x squared. So the 1 comes over, the 12 comes over. Okay, so I'm looking for two numbers that multiply to give us -12, combine us to give us a -1. That'd be -4 and 3. It's nice because we have a 1 here, so dividing by 1 doesn't change anything. Now I'm solving, so I get an answer of 4 and an answer of -3, but we can't assume that they work automatically just because I did the math right. Now we need to check for extraneous solutions. So if I plug in 4, I know 4 plus 12 is 16, and the square root of 16 is in fact 4. This works. Now I check -3. -3 and 12 is 9. The square root of 9 is 3. The square root of 9 is 3, not -3. So this is an extraneous solution. There is only... Okay, so here we go. So I'm going to find a unique value of x that when I plug it in, the right side will equal the left side. We're asked to solve. This is like number 8 from the review. I'm going to start by moving the 9 over to the opposite side. 3 equals x minus 4 raised to the 1/3. Now to isolate this x, I have to raise everything to the reciprocal. Reciprocal of 1/3 is 3 over 1. And 3 over 1 is the same as 3. So I bring down the x minus 4 on the right, and now 3 to the third. That means 3 times 3 times 3. 3 times 3 times 3 is 27. Add over the 4, and now I do need to check to make sure that this is correct. 3 minus 4 is 27. 27, the cube root of 27, that means what times itself 3 times gives you 27? That is 3. And 3 plus 9 is in. We're going to skip ahead. Students in the class in front of me have asked me to do a problem like 13. We'll do a couple like that. So I'm just going to go over what 13 looked like. This was 13. It asked us to identify the inverse and then to go back and identify the actual domain of the inverse. Now, it does say in this original problem to only have x is greater than 0. So keep that part in mind. Okay, so here's what we're going to do. We know that this is a y, right? And so when we find the inverse, we switch x and y, and then we simply isolate the y. So first I move the 2 to the opposite side, and then now to get the y by itself, the opposite of squaring is square root, and of y equals the square root of x minus 2. Okay, as a quick reminder, if this is m, and let's say we have m inverse, remember as a quick reminder, if you forgot this from freshman year or first semester, that when we discuss the input and the output, the input of the normal becomes the output of the inverse, and the output of the original becomes the input of the inverse. So keep that in mind. So when you see this, and it's a link to the original, and that's linked to the original, so this is x, this is my input. Okay, so maybe if you have the paper in front of you right now, you're going to go to actually where it says x is greater than 0 on the paper, write input there. So that's input of the original. So input of the original becomes the output of the inverse. So here's what I'm going to do. I'm going to take this and I'm going to graph it. So I'm going to come up here, go up to Desmos, and I'm going to graph what we have. So we have y equals, and we're going to find the square root by coming down here. There's our square root of x minus 2. So here's what I have. And now I need to be able to provide what is the domain. So it starts at 2, and it continues to move to the right. It starts at 2 and it moves to the right. So how can I write that? So it includes 2. So the domain here of the inverse, and I should put m. That's the original function. The domain for this particular problem would be 2, and then we move to the right. Okay, let's practice another one like it. So f of x equals x squared minus 5. So let's do the same thing. Let's figure out the inverse, and then let's figure out what is the domain of the inverse. So here's y equals x squared minus 5. Okay, switch the x and y. So x plus 5 equals y squared. Take the square root, and this is going to be the inverse. So I'm going to write it correctly. The original function was f, so here's the inverse of this, and it's the square root of x plus 5. I'm now going to go in here, and I'm going to plug this in. Come back up here, this is x plus 5. Okay, and now if I have to state what is the domain, okay, it starts at negative 5 and it moves to the right. Starts at negative 5 and it moves to the right. How do I identify that? Starts at negative 5, I include it, and it moves to the right. So I'm provided with two basic functions, and I'm asked to prove using composition of functions that these two equations are in fact inverses of one another. This is like problem 14. So what we're going to do is composition of functions. It looks something like this. We're going to check that, better than equal x, and then we're going to also come back and check this. So I'm going to start by writing g down. I'm going to write g down. So, but whatever I see in x, I'm going to leave a big blank spot. Okay, so I put down g, but then inside of g, wherever I see an x, again, I leave it blank, and I substitute that space with what f of x is equivalent to. Square root of x plus 3. Okay, so The square and the square root, again, they don't just disappear, they simplify to 1, and I bring down x plus 3 minus 3. These two are going to add up to 0, and I'm left with just x. So I did g of f of x, and it worked out. Now we have to show both ways in order to verify they are in fact inverses. Now I do f of g of x, which means I write down what f is, but wherever I see a parenthesis, or sorry, wherever I see an x, I leave a parenthesis. Now inside where that x was, I'm going to replace it with g, x squared minus 3. Okay, here we go. The negative 3 and positive 3 add to 0. And then the square and the square root simplify to 1. And I just proved, using composition of functions, that these two are in fact inverses of one another.